All right. Thank you for this opportunity to talk about some of the behavior of groundwater surface water interactions, and more specifically some of the dynamic behavior that we're learning about that exists within the Carson River watershed. This presentation is somewhat technical, but I'm going to do my best to be effective in communicating the concepts. But I want to make sure everybody knows if they're not quite getting something or have some questions, please feel free to ask questions after this presentation concludes. So this particular talk is about the behavior of stream capture under varying flow conditions. And these are dynamics that we've been studying and learning about through this Humboldt capture study. And before I move on, I want to make sure I acknowledge that my co-authors. Steve Jepsen is a volunteer in our office, and he's the one who's been working on this particular problem mostly. And he's provided a lot of the content that we're going to look at today. And then I also want to recognize Kyle Davis, who is the principal modeler for the Middle Humboldt model, the capture model. So, and the last thing before moving on is that the results we're going to show today are provisional and they're subject to revision, and we plan to eventually publish this in a journal article. So to begin, I want to make sure everybody's on the same page as far as what is stream capture. And so by strict definition, stream capture is the reduction in stream flow that's caused by a pumping well. And so to help illustrate this, the panel on the right shows the physical process that occurs and what the source of water is to a well when it's being pumped. The top panel shows a system, a hypothetical system that's in a dynamic equilibrium. Of course, there's no pumping going on, no changes in storage. All the recharge is going to discharge. Some of that discharge goes to ET through phreatophytic or riparian vegetation, and other discharge goes to streams or springs. Now, the second panel there shows a well being introduced and starts pumping. And when a well first starts to pump, water initially comes from storage, from groundwater storage from adjacent and around the well, and it starts to draw down the water table. And as time proceeds, as we move to the third panel, that drawdown continues to go down, but it starts, the cone of depression starts to reach out and starts to impart gradients towards other boundary conditions such as streams or towards that phreatophytic vegetation. It starts to lower the water table below the phreatophytes, and when the water table is lower below phreatophytes, they're not able to use as much water, so that becomes a form of capture because you're taking that water away from the phreatophytes. But it also can reduce the outflow to stream or increase the recharge from the stream to the aquifer in order to supply the water to the well. And then eventually it reaches some dynamic steady state in which the storage is no longer changing and it's getting a fraction of its flow to the well from the streams and from the capture of ET. So this is also expressed in the chart on the left, and this is what we call a capture curve or capture curves, and it shows the same behavior, but it shows it more graphically. Basically at time zero, when you first start pumping a well, all the water comes from storage, or 100% of the pumping is coming from storage. And then as time goes on, less water is coming from storage and more is coming from stream flow capture, and then also from ET capture. Now, an important distinction I need to make for the rest of this presentation is that we refer to, the USGS refers to stream capture as stream flow depletion. They're the same exact thing, but the USGS prefers the nomenclature of stream flow depletion. So how is stream flow depletion determined? Well, there's several methods that can be used to solve for stream flow depletion. The first method I'm talking about here is to use an analytical solution to the groundwater flow equation, such as Glover's solution, which is shown right here. In order to have a nice, clean analytical solution like this, there are a lot of assumptions that need to be made about the system. And for the Glover's analytical solution, the assumptions are that the aquifer system is infinite in extent. The aquifer is confined and it's homogeneous, or it has the same properties for permeability and storage throughout the system. It is not allowed to vary. And for the streams in the system, they must fully penetrate the aquifer. They need to be straight, and you can only be one stream. And also that stream must have a perfect connection with the aquifer. So the Glover solution is useful in many applications, especially for single well analysis near a river. But once you start looking at entire regions or watersheds and multiple wells, you start to deal with the breakdown of the assumptions, especially with the simplified geometry as well as the assumption of the homogeneous conditions of the aquifer. And so when that happens, the Glovers and other analytical solutions can no longer be used, and another method must be used. And so for many instances, groundwater flow models are really the only option or the best option for determining stream flow depletion, because groundwater flow models allow for complex boundary geometries as well as for varying aquifer properties, which are generally determined through the process of model calibration. And then once you have a calibrated groundwater model, it can be used to estimate stream flow depletion at all locations of interest within the model domain, as well as through the time. And these can be color-coded up in what we call capture maps, and this map on the left is an example of a capture map developed for the San Pedro Basin in southern Arizona for the stream flow depletion that would occur after 50 years of pumping. And so what you get from a groundwater flow model for any given location is really these capture curves, or this relationship between the pumping at that location and the capture of stream flow or springs of interest. And generally you get these nice smooth curves because constant flows are being used to run the models. And so that's generally the character. And you can see that the character of stream capture varies with distance from the river based on the properties of the system. And in this particular example, I have two wells. Well A is near the river, and it has a much more rapid response, or you could say that stream flow depletion occurs much more rapidly, quicker in time. Whereas a well further away from the river, or in a unit that's tighter, has less permeability, that the time to capture takes a lot longer. And so you get a more subdued stream flow depletion curve like shown right here for well B. So why is this of interest, and what are we trying to do here with this presentation? Well, we know that we're looking at stream capture using models, typically just using a single stream flow value, and we get these nice smooth curves, stream flow depletion curves. But we have a lot of smart water managers out there who know that our groundwater systems that are connected with a river tend to get replenished during high flow events, especially during flooding events. And they wonder, they have questions on how the stream flow depletion works in these cases. So does the varying flows affect the magnitude and the timing of the stream depletion? Can high flows offset stream depletion or reset it to some previous level? Or another really good question, is depletion different during different climate times? So is it greater during floods or is it lower during drought? And so that's what we're attempting to address with this presentation, is to kind of look at the characteristics of stream flow depletion under these varying stream flows. So we test these concepts using a hypothetical model. This slide shows the hypothetical model that we used. It's really just it represents a relatively simple aquifer system. It's about 6 miles wide, 20 miles long. It's a half a valley with the river running down the middle of the valley, which is the edge of the model. There's groundwater recharge occurring from the mountain front. And then there's a river flowing along from the left to the right. There's 6 wells embedded in this model that we pump to test these concepts. And so what we're doing here is taking a look at the stream flow depletion that occurs under different river conditions. So on the left side, we show the tests that we did for constant river flows. And we test the various percentiles of flow, the 10th, 25th, 75th, and 90th, and the 50th percentile, which is the median. And then we also look at the average flow. So we'll take a look at that. And then we also take a look at a system that has a river that actually fluctuates as you would expect to occur in real life. And so this shows the hydrograph that we used in the test model. If you look at this hydrograph, you can see it looks a lot like one of the rivers around here locally. This is actually the Carson River at Carson. It shows, we have these really big wet periods like 1983, 95, 2006, 2011, 2017. And then we also have our drought periods in the late 80s and early 90s, the early 2000s, and then again from 2012 through 2016. On here we show the orange line represents the average flow, which is 400 CFS, as well as the green line, which represents the median flow of 188 CFS. As most folks are aware, the average flows for rivers tend to be much greater than median flows because they're leveraged by flooding events. So this shows the results for the analysis of stream flow depletion under the different magnitudes of constant flow. And what we see is that the stream depletion does vary depending on what constant flow is chosen. And what we see is that for the 50th percentile, the 75th percentile, 90th percentile, they don't vary that much. But as we start to get into really low flows below the 50th percentile, we start to see a remarkable drop off on the amount of stream flow depletion. So the gist of this slide is that it does matter what the flows are that you're using as far as what that stream flow depletion is. So this slide shows the stream flow depletion under the varying flow conditions associated with the use of the hydrograph. And you can see that there's a lot more substantial variability than associated with the median depletion curve and the average depletion curve. Also shown on this chart is a 5-year moving average just to get a sense of how the long-term variability is associated with that varying depletion curve. So the gist of this slide is that stream flow depletion under varying flow conditions is actually quite variable, but does kind of bounce around or center around the smooth depletion curves. So this slide is showing the same information that was presented in the previous slide, but it's showing it in terms of the cumulative capture over time. And this is a great way to look at the overall results because this lets us look at how the differences between the different curves add up over time. And so we can see what those differences look like over time and what the bias is between the different approaches. And what we see here is that the varying flow depletion curve is very similar to the median depletion curve. And so we've looked at this result in many different instances, and what we're finding is that the median depletion curve does a good job at representing the overall depletion under varying flow conditions. So now let's look at the behavior of stream flow depletion for a well near a varying flow river. So as you see on the right here, we have a chart showing the median stream flow depletion in green as well as the more varying stream flow depletion associated with the varying flow river in blue. And what we see for this particular site being right next to the river, it becomes depletion dominated rapidly, which within just a few years it gets up to almost 50% of the source of the water to this well comes from the river. But what we also see is that this large variation in depletion is dependent on the magnitude of the change in the flow, but it generally centers around the median flow depletion curve. And in this example, we're looking at a well away from the varying flow river, and we see it has a much more prolonged response. The stream flow depletion has a much more prolonged response in time, and that the varying depletion curve around that median curve tends to be much more subdued earlier in time, and then as depletion ramps up over time, the magnitude of that variation grows, and then over time it just continues to center around that median curve. So the point of this slide is to demonstrate the timing of streamflow depletion with the variation of the streamflow itself. And unfortunately, this was a video that had a dot that ran along the curves so you could see them running together. But unfortunately, it appears that videos don't work when you're recording in PowerPoint. So I'm going to just do the best I can to explain this. So what we see is that when the stream depletions are higher than the median depletion curve, what we're seeing of the stream flow is that's during periods when stream flows are high or increasing rapidly, and then during periods when stream flows are decreasing or low, that's when we're seeing that the streamflow depletions are also lower than the median curve. And so this is good news because this indicates that depletion rates are higher during when the rivers are higher and there's more water available, and they're lower when the rivers are low and there's less water to go around, and so there's less of an impact during those conditions. So when we generate these streamflow depletion curves from the models, they're generally the smooth curve shown here on the left side in black. And we also know from earlier that it's best to use the median streamflow to determine that streamflow depletion curve. But we want to be able to somehow represent that deviation of the depletion from the median depletion curve in a more realistic manner so that we can count for the timing differences of depletion based on the variation of stream flow. And so what we're looking at here in the next several slides is a method that we've been working on to try to be able to estimate that red curve on that left side by using the characteristics of that median curve, that median black depletion curve, as well as the stream flow hydrograph shown on the right. So we explore this method development using the Middle Humboldt River Basin model. As most folks are aware, there's a big capture study going on in the Humboldt River Basin. There's 3 models being developed, one in the lower, middle, and upper basins. And a more complex model that's being developed is in the middle basin, and that's the one that we have the dynamic stream flow incorporated into the model. This figure on the right just shows a conceptual diagram of the different processes and hydrologic water budgets being included in with the model. We have been testing the regression on wells located in the Middle Humboldt Basin model in an area near Winnemucca. Area 1 is further away from the river. We choose a well that's further away from the river, has lower depletion rates, and then from area 2 for a well that is closer to the river that has much greater depletion rates. And so this slide shows the results of the method development where we're currently at. And what we're showing here is the red curve is the simulated depletion based on the actual hydrograph. We refer to this as a truth. This is what we're trying to reproduce. And we're trying to reproduce this using the median streamflow depletion curve shown there in the black, as well as the actual hydrograph for the Humboldt River at the Palisade gauge. We run those together to generate the blue curve, which is the estimated curve, varying depletion curve. And we're having mixed success. The method currently is doing a good job at estimating the variability of the streamflow depletion around and near the median depletion curve, but we're not quite hitting the highs, the extremes, the highs and the lows that are shown there in that red curve. Keep in mind that this particular well is away from the river and has a fairly low depletion rate. You can see after 55 years, we're only looking at about 7% of the pumping is coming from the stream. So now looking at the lower curve, that's the cumulative streamflow depletion over time. This kind of gives us a sense of how well it's doing and what's the bias between the two methods. And we can see that the red line again is the truth in this case, and then the blue line is the estimated depletion curve based on the regression that we've been developing. And there's really almost no bias between the two because what we're missing on the highs and lows are basically canceling each other out. So now this slide is showing the same analysis, but it's for a well from area 2, and it's much closer to the river, has a much higher fraction of depletion from the river. And what we see here is pretty much similar results. We're reproducing the variability of that varying depletion curve around that median curve pretty well, but we're not quite getting the extremes. And there's a lot more cumulative streamflow depletion occurring at this site, and so we do see a little bit of departure between the estimated depletion and the simulated varying depletion, but it's pretty reasonably close. So preliminary results of this work indicate that the streamflow depletion under constant flow can vary with the magnitude of the constant flow, and that the median streamflow value is the most appropriate streamflow value to use to calculate the streamflow depletion. And also, under varying flow conditions, we also learned that streamflow depletion can fluctuate by a fair amount, but the good news is that the depletion rates are higher during high flow conditions, especially high flows and floods, and that depletion rates are a fair amount lower during low flows and during droughts. But when you look at the cumulative depletion over time, it's really similar to the estimated stream flow depletion from the median stream flow value. So next steps for our work is to continue refining this method to see if we can improve our estimates of the deviation from the median depletion curve, and to see if they can't improve those results a little bit. And then also to investigate the varying depletion with the water rights that are in priority, because the timing is very important as far as water rights and understanding conflict. And then also to see if we can't come up with an alternative approach for estimating the deviation of the stream flow depletion that's more directly based on a correlation with the deviation of the hydrograph from the median flow in the hydrograph. So that concludes the presentation. Really thank you for your time, and there will be time for questions. I just want to conclude with a few resources. The USGS Nevada Water Science Center Carson River Basin page is right there, and then the Humboldt River Basin page is at that link below. And then lastly, just want to highlight this publication. A lot of people already have this, but for a better understanding of streamflow depletion, there's this great circular that's at this website. So thank you much. I'll be glad to take any questions.